So this is question number 5 on the Canadian Senior Math Contest 2021. And this one is asking for the solutions where all your numbers x are greater than 0 for which this equation holds true. Okay, so to solve this question you have to be able to use logarithms. You have to know the logarithmic laws and be able to manipulate those. Okay. So let's just analyze this question, analyze the domain of x, and yeah. So we're just making observation that if we have a log function where we have a base b and some input a, the base will have to be a number that's greater than 0. Since it's an inverse exponential, we typically work with bases that are positive, and then it's also not equal to 1 because now be maybe silly and maybe trivial and won't represent our typical logarithmic function. And then the input, the domain of the logarithmic function, since it's an inverse exponential, it's always going to be greater than 0 if we want a valid output. Okay, so based on that fact, we can look at these, the places where x are, and say that x will have to be greater than 0 and x is not equal to 1. Okay, so now let's introduce a second property of logs. And this is the case where we have base b, some input a with the raised to exponent c, where c is a constant. Okay, and so this is going to be equivalent to the c. We move it to the front and multiply that by whatever is inside the log function. And so that's the second property of logs. The power log 3. Okay, so we'll make use of that fact and rewrite this equation. So we have log 2 and we have x to the exponent 2, so we can move the 2 to the front and have x on the inside. And then you notice the 8, we can actually rewrite that as a power and as t cubed. So we can move the 3 to the front and multiply that by 2. So that's going to give us 6 log base x 2. And then that's going to equal to, we move the 3 to the front and multiply that. So we have 3 log base 2 of x. And then we can also rewrite 32 as 2 to the 5. So we move the 5 to the front and multiply that with 20. So 520 gives us 100. And then we have log base x of 2. Okay. So now we have this sorted out. And now let's introduce another property of log. And this comes from the fact that logarithms are inverse exponential functions. Okay. So let's say that the output of log 2 base x of log 2 base x is going to be some number y. Okay, and this holds true if and only if 2 to exponent y gives us x. Okay, and then we can do the same thing for log base x, log base x of 2. And let's say that equals to another output, we call it yard. That holds true if and only if x to the yard gives us back 2. Okay, since logarithms are inverse exponentials, we can convert freely between logarithms and exponential form. Okay. So let's make another important observation where 2 to the y is equal to x. Okay. And then over here we have x to the other is equal to 2. So what we can do is actually replace x with 2 to the y over here. So let's do that. 2 to the y to the power of z is equal to 2. And using your grade 9 knowledge of exponentials, we can actually multiply these. So 2 to the y and z gives us 2. Okay. And then we make another important observation. They have the same base. So what this means is y multiplied by z is equal to 1. Okay. And so let's say that y is equal to 1 over z. Alright. Now let's go back to this part. Okay, and let's start replacing these terms with y and z. So with 2 log 2 base x log base 2 of x, that's going to be y. So 2y plus 6, this is going to be z is equal to 392 all over 3 times log 2 of x is going to be y. And the next one is going to be z. Okay. So we make this important observation. Alright. Y and z, since they are the output of the logarithmic function, y and z are just gonna be in a set of real numbers with no restrictions on them. Okay. Other than the fact that 3y and 100z is not equal to 0. And we'll make an assumption that's the only condition that we'll impose so that we can actually simplify and multiply the denominators and rationalize the whole expression. Alright, so we have this. So what we can do now is we can actually rewrite the whole expression in terms of z. So we replace y with 1 of z from earlier. So 3 over z plus 100 over 100 times z times 2 over z plus 6z is going to be 392. Okay. And then we can just simplify, use the distributive property and expand. So 3 times 2 is 6, z squared, and then 3 times 6 gives us 18. The z's are going to cancel. Assuming that z is non-zero, we should also impose that restriction as well. And then we have 100 z plus times 2, so that gives us 200, and the z cancels. And then we have 6 100, so that gives us 600, and then z squared, and that gives us 292. Okay, so we can actually combine these like terms and clean things up. So 6 over z plus 218 plus 600 z squared is equal to 392. Okay, now if we assume that z is non-zero, then we can actually multiply the whole expression. Oh wait, I've got to carry down the z squared on over here. Okay, so the whole expression, assuming z is non-zero, we can multiply by z squared on all the terms on both sides. So we have 6 plus 218 z squared plus 600 z to the 4 is equal to 2 z squared. And this rationalizes the whole expression once again. Okay, and so you'll notice that these two terms are like terms, so we can subtract. So 6, so we have 6 minus 174 z squared plus 600 z to the 4 is equal to 0. And if you notice, this is actually a quadratic expression, right? And if you also notice, these terms are these terms all share factor of 6, so we can actually factor the 6 out. So we have 1 take away 29 z squared plus 100 z to the 4 is equal to 0. Okay. And since we have a quadratic, let's do this. Let a be equal to z squared. Okay. So we have 100 a squared, right? A squared gives us z to the 4. And then we take away 29a with a z squared, so we take away that. And then we add 1, the constant term, and that's going to be 0. Okay. And this expression is actually factorable. So we can factor that into 4a take away 1 and 25a take away 1. And that's going to be 0. Okay. So that means the solutions, the possible values of a that we get, is not a is equal to 1 over 4, or a is equal to 1 over 25. Okay, we're almost there, we're still not done. So since a is equal to z squared, we'll just do this. Z squared is equal to 1 over 4, or z squared is equal to 1 over 25. Cool. And so we want to get z by itself, and if we want to do that, we have to take the square root of both sides. Wait. So we take the square root of both sides. That means the answer will be the absolute value of 1 over 4, or 1 over 25, whatever that is. Since z squared is always going to be positive, right? Okay. And we can, well, you can always write plus or minus, same thing, same idea. And then we'll simplify that. So the square root of 1 is 1, and the square root of 4 is 2. So plus or minus a half, or plus or minus 1 over 5. Okay. And then we'll be very close. If you remember that y is equal to the reciprocal of z from earlier, over here, we'll make use of this fact and get x. Okay, so y is equal to the reciprocal of z. So that means the possible values of y that we have are the reciprocal of this, so plus or minus 2, or y is equal to the reciprocal of that, which is going to be plus or minus 5. Okay, and then going back to the last piece of the puzzle, where we defined y as an if and only if statement where 2 to the y gives us x. Okay, so 2 to the plus or minus 2 is going to give us x, or 2 to the plus or minus 5 is going to give us x. Okay, so that means the possible values of x that we have are x is equal to 2 squared, 2 to the minus 2, x to the positive 5, wait, not x, 2 to the positive 5, or 2 to the minus 5. And those all fit within our original construction that x is greater than 0 and not equal to 1. So that means x can either be 1/4, 4, 1/32, or 32. And that is the answer.